cheap like the 741, but it'll provide amplification. Okay, so we have already talked about how we can look at the MOSFET when it's in the saturation region. We can look at it as a voltage-controlled current source, where the current source behavior is between the drain and the source. This is essentially where your current source would be, and the voltage control is your VGS. Okay, so how can we translate a voltage-controlled current source into a voltage-controlled voltage source? That's all really an amplifier is, right? An amplifier is a voltage-controlled voltage source where we can have some sort of manipulation over what the coefficient is between the input and the output. So already, without doing anything, this makes a pretty good transconductance amplifier. But we want a voltage amplifier. So how do we do that? We add an external source and a resistor. And so originally we had control over ID. Now we have control over VDS, which is the voltage output. If you think about this as an amplifier, you can think of this as the input, okay? The signal that we're going to be amplifying, and the output is going to fall between those two terminals. So input is inside of here because VGS will have an effect on ID. Output is here, which is our VDS. All right, so what does that VI relationship look like? So let's say I were to graph, and I have the graph here. Let's say I were to graph VGS versus VDS. What would that relationship look like? So on the x-axis is the quote-unquote input, the value we're trying to amplify. And on the y-axis is the output, the amplified value. What would be the best? The best would be if it looked exactly like this. Right? That would be great, because then our gain would just be the slope of whatever that line is. And this is the type of a relationship you have with, like your 741s and all that type of stuff. But as you can see here, right, that's not the case. The input-output relationship is more nonlinear. And so there's three different regions that we can essentially talk about. And what we're going to do is move from left to right along the x-axis. So first things first. When VGS is 0, up until when VGS is equal to VT, the overdrive voltage is 0, right? That means that the switch is completely open. There's no current going to be flowing. And so the output here, this voltage will be equal to this voltage, right? When VGS is less than VT, the circuit is open, no current flowing, no voltage drop across this resistor. This voltage equals that voltage. So for very small values of VGS, that's why you see here VDS equals VDD. Nothing's happening. Next, then we enter the saturation region. Why is it going to be the saturation region? Because initially the value of VDS is going to be really big, right? VDD most times is going to be 5, 10 volts, okay? So initially VDS is really big. It's bigger than VOV. And we're in the saturation region. Now, what happens as we continue to increase VGS? As we continue to increase VGS, the switch, if you think about the transistor as a switch, the internal resistance is getting smaller and smaller. It's closing more and more, okay? And so if we go back to the circuit, this allows more and more current to flow through between the D and the S terminals. More current flowing this way, bigger voltage drop across RD, which means that you would expect that voltage to go down, right? If I were to draw here on the board the same sort of graph that is in the notes, this is VDS. If I were to draw ID, no, actually that shape's not exactly right. I'm just going to draw it linearly. It'll go up. It'll increase, right? So the more that the current increases, the more that the voltage VDS will continue to drop. What happens right here, eventually VDS will get smaller, it'll get smaller, it'll get smaller, and it will reach the point of being equal to VOV, right? Yes?
Why is VDS dropping?
VDS is dropping because as you increase VGS, that's the equivalent of closing the circuit, making the internal resistance between these two terminals smaller and smaller, which means more and more current will flow down here. What is this voltage? VDD minus ID times RD. As ID gets bigger and bigger, VDS gets smaller and smaller. Eventually, we'll get to the point where VDS is equal to VOV, and it'll switch over from saturation into triode, and then we get the rest of it. It'll continue to close, the current will get higher and higher and higher, and then eventually the current will get so high that there'll be no voltage left across the DS terminals. The drop will all be across RD. So if you look here, the red bullets, those are just the different equations we use in the different regions. It doesn't say anything you haven't seen before. For all of the different regions, V out equals VDD minus ID RD. That works here, that works here. It also works here. Although because ID is 0, we could leave out the second chunk. VDS is, this should be less than VOV. Can I fix that here? Okay, VDS is less than VOV when we're in triode. VDS is greater than VOV when we're in saturation. And over here, I put VDS as question mark VOV. The only reason why I say that is because when it's in cutoff, there really is no overdrive value. Remember, we said that the overdrive voltage can't go below 0. So in this region, the overdrive voltage is actually undefined. Okay. This equation here, this is the ID, the VI relationship for triode region. This is the VI relationship for saturation region. And in the cutoff, ID is equal to 0. And then this is always the same. Overdrive voltage is VGS minus VT. Okay? So, not really any new material in those bullets, but I wanted to, because when we do these amplifier-based problems, sometimes it helps to have everything in one spot. So what we have here is there's two different cutoffs that we have to worry about. There's the cutoff of the FET, and that's when the FET completely opens up and doesn't allow any current to flow. And then there's the cutoff of the amp, which is when the voltage drops to 0. And that's the opposite. There's so much current flowing that the voltage VDS has dropped down to 0. So there's a sort of an inverse relationship going on there. The amplifier will be putting out the maximum voltage when there's minimal current, when the amp is opened up, and then vice versa. Okay. There's a couple of important points that we can define. One of the important points, so let me give you a preview. And I think I've already said this. The amplifier is going to be operating in the saturation region. So point A and point B are really important. Because if we're defining how this thing is going to work, we need to figure out component, parameters, inputs, whatever else we're going to be defining. We have to make sure that that maintains operation between here and here. How do we know where A is? A is pretty easy because A is just going to be where VGS is equal to VT. That's an easy one. Point A is easy to define. Point B is not necessarily so easy to define. It's the transition between saturation, which is here, and triode, which is here. And so there's two equations we can use to calculate that. 532, well, 532 is an equation you've already seen, and then 533. So all this is saying VDS equals VDD minus ID times RD. We've used this equation a million times. We know we're at the edge of saturation in triode, so we can use either one there. We'll use the saturation region equation. And now we go back and we solve for our value of VGS. And so what we see is that the value of VGS right here at point B, and this is the point at which VDS is equal to the overdrive voltage, we can use this equation. And that's just an inversion of what's shown above. So when we're talking about using the amplifier, we need to stay between point A and point B. We need to stay between VGS is equal to VT on the low end, and then on the high end, we need to stay below this, where VGS is equal to this value, given by the equation. All right? Now, what I'll stop and close on is that we don't want to use the whole range between A and B. We want to use a smaller range within there. So A and B are sort of like the absolute maximum values. It's like the two edges of the road. You could be driving on the edge of the road and still not be doing a good job, but the edges are the absolute boundaries for where we do not want to pass. And then we'll narrow it down from there and make a voltage amplifier. We are going to add an external DC source and this resistor here. So then what we end up with is, I don't know if the equation's on the sheet, it is. So VDS, which is the output, is equal to VDD, which is the external DC supply, minus IDRD. ID ultimately is controlled by the input, which is VGS. And so, right, we have an output, that's a voltage, as well as an input, that's a voltage. Now, this graph, again, what does this show us? This is the VI relationship for that circuit that's on the previous slide. There's 3 or 4 regions of operation that we have to be concerned about. There's the cutoff of the MOSFET itself when VGS drops below the threshold voltage. The MOSFET opens up, no current will flow. The output will be equal to VDD. Saturation region, when VDS is greater than VOV, that's between points A and B. Then we enter triode, and then we have this region, which is called cutoff of the amplifier. So we have cutoff of the MOSFET, and we have cutoff of the amplifier when the voltage is dropped to 0 at the output, meaning that there's so much current flowing that 99% of it falls across the resistor RD. We went over these equations last time. the main takeaway here is that we are going to be designing our amplifier to operate solely in the saturation region. So we need to stay between points A and B. And then second off, which we haven't talked too much about, is linearization. So we want an input-output relationship for our amplifier that's linear. You buy an LM741 off the shelf, and you get a constant gain of 5 or 10 or 15. So if we were looking at this as V in versus V out, right, it would be a straight line. We don't have exactly a straight line here, and as you get closer and closer to the edges, it becomes even less straight or more nonlinear, which is going to be a problem, but we're going to address it. Okay, these equations I believe we also talked about last time. This is the relationship between the output and the input voltage. Same equation from 2 or 3 slides ago, except now we substitute in for ID with the actual VI relationship for the MOSFET in the saturation region. And then this down here gives us the value of VG at this point B. The point A is relatively easy because we know that VGS will be equal to VT, the threshold voltage. That's when you hit A. And then for B, it's going to be the boundary between saturation and triode. And so VDS will be equal to VOV at that point. Okay, so if we use some algebra, we end up with this definition for VGS at point B. VGS at point A is equal to that. All right. Now, how can we linearize this voltage transfer characteristic? You'll see these 3 letters used, VTC, VTC. What does that mean? Voltage transfer characteristic. Another word for saying the transfer function for the device that we're working with right now. And so the way that we're going to linearize it is a lot like the way we linearize a function. We're going to pick an operating point, and we're only going to allow our input to vary a small range around that operating point. So let's say, there's a marker here somewhere. Let's say that we wanted to amplify a signal that had an amplitude of 50 millivolts. So if we just supplied the 50 millivolt sine wave, I'm just using that for example, directly to the VGS terminal, it would be here, right? Which is not in the saturation region. But what we could do is, like we did with the small signal model, we could have a time varying component or a dynamic component, and we could also have a static component, right? Or a large signal and a small signal component. So if we take our 50 millivolt sine wave and then we add to it a DC offset of whatever the value is that we need, let's say 0.5 volts, and then now our VGS, the small VGS, fluctuates around the linearization point. And you can see here, right around this point Q, which is the operating point, they also call it the, I'm not even sure how to pronounce it, quiescent point. It looks something like that. But we can go ahead and just call it the operating point. So right around the operating point, right, this is relatively linear. Okay, so again, we're going to apply the small signal model, and that is going to help us achieve the linear amplifier behavior. That makes sense. There's some drawbacks, right? We're really limiting how we can use this amplifier. We can't amplify any signal that's larger than we can apply the small signal model to. So we can't, the way we're building this amplifier right here, we can't take a 1 volt sine wave and amplify it by 10 times, okay? It's going to be restricted. The amount of gain that it'll generate can be pretty big. So, I mean, it can take the 5 or 20 millivolt sine wave and create a 5 volt output. But the magnitude of the input is going to be relatively limited. And we'll play around with those values when we get to some of the examples, and you'll see what you can and can't do. Again, this is really the most basic type of amplifier. So if you want to build something with a wider operating range that has a more robust voltage transfer characteristic, then you're going to need to use more than one device and some more advanced design techniques. So that's how we're going to linearize it. We're going to pick an operating point, and we're going to have our input vary around that operating point over a small range. So this point Q is the bias point, the DC operating point, static operating point, large signal operating value. And like I said before, it helps us because it puts us on a point of the curve where the transfer characteristic is relatively linear. Okay, so how is linear gain achieved? Let's get into the nuts and bolts of exactly how we're going to do that. We're going to apply the small signal model again. The basics of it are the same as when we applied it in Chapter 4 to the diode. We're still going to split the circuit from the total value into the large signal and the small signal components. And we're going to analyze those pieces separately. It's going to be a little bit different now, exactly how we represent those individual circuits, but we'll get to that in a second. So we take VGS, we split it up into big VGS, the large signal component, and little VGS, the small signal component. And what we're going to do is we're going to superimpose the amplifier input on VGS. Same thing as we're just going to add them together. And so now the resultant VDS should be linearly proportional to the small signal component VGS. So in the same regard, VDS, which is the output, that'll have a large signal component and a small signal component. Okay? The large signal component is not going to be considered part of our output. It's going to be just a byproduct of our linear operating point. So when we input a signal that waves like this, the output, so if we project it onto the blue line, we'll get something that looks like that. The output is only going to be the small signal component of VDS. So we're just going to, the DC operating or the DC offset, we're just going to neglect that out. Okay? And that makes sense because the large signal component of VGS is also not part of the input. So whatever is not part of the input shouldn't be included as part of the output. And so that's all that it says here. The output is little v ds, and it's proportional to little v gs. All right. And as long as we pick a small, relatively small value of little v gs, its effect will be linear and we'll get linear amplification. And so here you can see an example of what I meant when I said the projection. So if you say little VGS looks like this, we take the dotted lines, we can project and see where it falls on the blue line, and then show it projected on the x-axis, projected onto the y-axis. So here's the one point, here's the other point, which means that the height will go from this to that. Right? The slope is going to determine how much amplification we have. If the slope is 1, then the width here would be the same as the width here, right? And if the slope is greater than, and actually here it's negative, so -1, or has an amplitude, an absolute value greater than -1, then it'll get larger and larger. So the steeper we can make that slope, the more amplification we'll have. And how do we control that slope? There's a couple things that we can do in order to manipulate it. All right, so now let's ask ourselves, what is the gain going to be? So, is that my computer? I've been having a problem with the fan. No, I don't care about the sound. My fan's been going crazy on my laptop. I'm trying to figure out if it's breaking. So, the gain. In order to calculate the gain, we need to find the ratio, or the ratio of the rate of change of VDS over VGS, right? But we're only concerned with the small component. So here, what we're looking for is the slope corresponding to the operating point. So for this analysis here, we don't have to consider the small signal component. And why is that? I want to explain. Because we're assuming that the slope is the same along this whole juncture. So if we're trying to find the gain, all we're going to do is find the gain right at Q. And when we're right at Q, the VGS is only equal to the large signal component. So what we're doing here is we're finding the derivative of the voltage transfer characteristic right at the operating point, and we're going to assume that that slope is the same along the whole region that we're operating in. So there you can see what is dVDS over dVGS, with the assumption that we're going to evaluate it at the operating point. So here is our VDS, VDD minus 1 minus I RD, or 1/2 Kn, etc., RD, over VGS. We take the derivative. This piece goes away. This squared will become a 2, which will get rid of the 1/2. And what we end up with is this. The gain will be equal to minus, what's the name of this variable? If you guys, it's definitely going to come up on a quiz or an exam now, because people keep forgetting the name. There's only 2 versions of it. Yes?
Transconductance.
You're on the right track. You got one part of it.
Transconductance process.
So this is the device parameter. Oh. And the way to remember, again, you have the process transconductance parameter and the device transconductance parameter. The device is more specific to that device, and it includes the aspect ratio in it. That's the one without the prime. So this is the device transconductance parameter. The process transconductance parameter is the more general one, and that one does not include the aspect ratio, and that's Kn prime. I mean, it's not a big thing. I get it, but I don't really ask you to memorize that much stuff in this class. So it's one of those things I think that you just, as a graduate, you should come out just being familiar with what that term is. Okay, so the gain of the amplifier is going to be dependent on 3 different things. The device transconductance parameter, the overdrive voltage that we use, and the value of RD. So we could play around with the gain by manipulating those values. And remember, this is the overdrive voltage for the operating point, not taking into account any of the small signal stuff. If we use a DC offset for VGS of 0.5, this will be Kn 0.5 minus whatever the threshold is times the resistance. So what observations can we make about the gain? It's negative, but we already knew that from sort of looking at the way that the voltage transfer characteristic was shaped. It's proportional to the load resistance. The device or transistor conductance parameter. Just use the terminology I've been saying. I know that is slightly different, the wording of it. And the overdrive voltage. And 538 is just another version of 537, which comes in handy sometimes. It uses some algebra to move to state it in terms of the large signal component of ID. It's in your cheat sheet. It may come in handy in some problems. Just another version of 537. So now how does 538, just want to see how my battery is doing, sorry. As I said before, my laptop is starting to do some weird things. So how does 538 relate to physical devices? For modern CMOS technology, the overdrive voltage is usually no less than 0.2 volts, or the large signal value that you'll be using to maintain in the saturation region will be no less than 0.2 volts. And this means that the maximum achievable gain you'll get is somewhere in the range of absolute value, 10 times whatever the VDD value is. Again, that depends on specifically what device you're using and some other factors. But this will be sort of like how for the small signal model in Chapter 4, we use that threshold of 5 millivolts per diode as being like, okay, if we're below that, that's okay for the small signal model. This is another sort of rule of thumb that we'll be using. So this does not mean that the output will be 10 times what the supply is necessarily. That's the maximum. So for example, if we have a 130 micrometer CMOS technology with a VDD of 1.3 volts, that yields a maximum gain of 13 times. Well, that kind of disproves the statement above it, but there could be cases where it's lower. All right, so let's get into our first amplifier example. Just looking ahead, is this one that we should break the iPad out for? No, I think the math on this one, yeah, we're still not in anything that's that mathematically difficult. So we'll just go through this in the slides. If you have any issues or questions about any step along the way in these problems, please throw your hand up. I mean, we haven't gotten many homework problems questions this semester, and you haven't gotten that many raised hands. I know I'm such a great lecturer that there's never any questions, but I joke, obviously. As we get into the end, this is especially difficult material, so if you're ever going to ask questions, make sure to ask questions here. This is where it's the culmination of a lot of what we've been doing in previous chapters. So consider an amplifier that's shown here. The transistor is specified to have a threshold voltage, a process transconductance parameter as shown, an aspect ratio of 10, and lambda equals 0. Again, what does lambda equals 0 denote? You guys remember that one? Come on. Yes?
Channel modulation.
Channel length modulation is neglected. Okay, so we can assume that the VI curve in the saturation region is flat. They also give us the parameters of the amplifier circuit. The external supply is 1.8 volts. The load resistance is 17.5 kilo ohms. And the large signal component of VGS is 0.6 volts. So they already are telling us where our operating point is and around what point we're going to linearize this. Now, for VGS equals 0, small signal component, find the overdrive voltage and the large signal components of ID, VDS, as well as the gain. So this is really just saying characterize the amplifier and tell us how this thing is going to operate. Now, because this is an amplifier, we can assume that it's in saturation region. with a fair amount of certainty. I still say that at the end you should go back and check to make sure that VDS is greater than VOV. If that doesn't end up being the case, you're sort of in a weird spot because then it's really not operating like an amplifier. So I would say that's not a question that I would give to you, but still check. All right, so let's solve this. We know that the current here will be 1/2 Kn VOV squared. Okay, so the different values we can find. The low-hanging fruit is going to be the overdrive voltage because we know what VGS is. They tell us that. And we know what VT is. So the overdrive voltage is 0.2 volts. That's easy. To calculate the large signal component of ID, we are just going to plug in our value of VOV. We know everything else. We know this, we know this, we know this, and that is the same as that right there. So the large signal component, I mean, I didn't use an uppercase I and an uppercase D, but I mean, in this part A of the problem, we're only considering the large signal component. So the large signal component of ID is 80 microamps. And does it ask us anything else? It asks us for VDS and AV. So for VDS, we're simply going to use the KVL-based expression. We know that VDS is equal to VDD minus RDID. This is given to us, this is given to us, this we just calculated. And so our VDS ends up being 0.4 volts. Let's test the assumption that the MOSFET is operating in saturation. Is VDS greater than VOV? Yep, that's good. And then lastly, we can go ahead and calculate the gain, which is this is equation 537 we just got from when we took the partial derivative of VDS with respect to VGS. And given, plug in all those, and we get a value of -14. So that is before we're trying to amplify anything. They're just asking us to characterize in general how this thing is going to work. Okay, so what does part B ask us now? So this is, I think, one of the more confusing types of questions that can be asked for the amplifier. More so than giving you the output and asking you what giving you the input and asking you what the output is. This whole issue of the swing. So all right. If we're here and they ask what the maximum swing is, what they're saying is, how far can I move in either direction and stay in the saturation region? That's the maximum swing of the input. So that's here to here and here to here. Normally, the maximum swing is the lesser of the two values. Maximum symmetrical swing. It's sort of like if I'm standing up against the wall, how far can I symmetrically stretch out my arms? This far, right? Even though I have room on the left-hand side, because I'm constrained on the right-hand side, this is the maximum symmetrical swing that I can do. If I'm standing out here, then my maximum symmetrical swing grows. Obviously, if I end up on the other wall, then I'll get held on the other side. So it's just the minimum distance between Q and A, and the minimum distance, or Q and A versus Q and B. The maximum swing in the output is going to be on the y-axis between Q and A and Q and B, but the easier way is you can always find the maximum swing for the input and then just multiply by the gain, right? And then I'll give you the maximum swing for the output. Although that's a little bit of an estimation because it's not completely linear. All right, so how do we do this now? We know we have to find two different numbers and the lesser of the two. So, what's the first expression? The first expression is saying that VDS has got to be greater than VOV. So we're starting off by looking at how far we have until point B, right? Because point B is the crossover between saturation and triode. So we want to see how far we can go until VDS stays greater than VOV, or in other ways we could say VDS is equal to VOV. All right. Now we want to get that in terms of small VDS. Because we know the large signal component, we know what VOV is, we want to see how far we can swing, which is that small value VDS. And so in order to do that, what we can do is move the knowns to one side. So we know the overdrive voltage, we know VDS. Then we'll split VOV into VGS minus VT. Then we'll split the total value of VGS into the large signal and the small signal components. And ultimately, what we want to do is solve for small VGS. Now what we can do is we can take VDS and replace it with the gain times small VGS. Right, we move things to one side. We substituted in our large and small signal components for the total VGS. Now what we want to do is make this equation something that we can solve in terms of only one unknown. Unfortunately, though, known, 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 unknown, unknown. So we have two unknowns. In order to get rid of that, we're going to substitute in for small VDS with the gain times small VGS, and now we only have one unknown. This we calculated before. These are both unknown, but they're the same value. Known, known, known. Right? So we can take the algebra, or we can use algebra in order to solve for little v, little gs. Take that, divide, and so we see that the swing of little v gs has got to be less than the large signal components of VGS minus the threshold voltage minus the large signal component of VDS divided by the gain minus 1. Here, be careful. Why does the sign switch? Right, because we're dividing by what we know is a negative value. AV is negative. So whenever you do that with the inequality, that switches the sign. Or it flips the direction of the inequality. And so when we plug in all those values, we end up with this result that VGS has got to be less than 13.3 millivolts in order to maintain us in the saturation region. Now, that's only checking one side, right? Remember we said that there's two sides that have to be checked. Normally, and I may tell you, if I give you a problem like this, I may tell you can assume that the constraint is on the right-hand side. The constraint is with regard to the edge of saturation and triode. That's normally the case. It tends to be closer to point B as compared to point A. So in this problem, they assumed that the distance to point B was smaller than point A. But let's go ahead and calculate the other one. So point A is the point at which VDS is equal to VOV. So VDS is 400 millivolts. VOV is, on the previous slide, what's VGS? So VOV is 200 millivolts. So the distance between them is 200 millivolts. So as you can see, right, the swing on the left-hand side is a lot bigger. You have plenty of room on the left-hand side. So the maximum symmetrical swing is determined by the distance between Q and B, which is 13.3 millivolts. And so that tells you how the absolute maximum of how big your swing can be. Now, that doesn't take into account the linearity of the function because, right, we said that worst case scenario, we have to stay in between A and B. But if we make our range too big, things will start to become increasingly nonlinear, and that'll hurt the quality of our amplifier. But they didn't take that into account in this problem. The other thing about this chapter is that they don't give you a threshold like they did for the diodes. In the diodes, they said if it's more than 5 millivolts amplitude per diode, you're out of the range. From what I remember, I mean, I might be proved wrong by the slides in a second, but I'm pretty sure they don't give you any sort of threshold like that in this. So we're going to be using as our constraint or our requirement just staying in between A and B. Okay. So that's a really good amplifier-based problem. And like I said, the swing ones actually are probably harder than the other types. So we're going to go through a lot of the same methods that we talked about with respect to diodes, and we're going to apply them to MOSFETs and amplifiers. One is the graphical method. So we can use the graphical method to solve for the solution of a transistor, a FET-based circuit. It's going to be done in the same way that we did for the diode. We're going to draw one line, which is going to be the load line. That's the straight one. Okay, which is going to be dependent on VDD minus so ID is equal to VDD minus VDS over RD. So that's your slope. Then, whereas for the diode, we had the exponential VI curves. For the MOSFET, we have the triode saturation, the curves that we're used to seeing. So you would graph both of them and try to find the intersection between them. I'm not going to ask you a graphical method problem for MOSFETs. Okay, it's going to be really way too difficult to graph. But at least you're familiar that it's an alternative. And again, like I said, before we had computers to do everything, graphical method was a lot more attractive. Now, not so much. Okay. So now, in the previous problem, they gave us the value of Q. They gave us what the bias, the operating point, or what we have called in the past the large signal operating point. But how do we determine it, right? If you're trying to design an amplifier, what do you just pick the middle, halfway in between A and B? We know that's not the case. I mean, at least in the example that we looked at, because it was so much closer to B than it was to A. So there's two considerations that we have to take into account. Okay? One of them is the required gain, and the other one is the swing at the output. Because if you take a look here, you'll see that as the operating point approaches B, the gain increases. It starts to get more slope. The slope starts to get a little bit steeper. But as you get closer to B, your maximum swing is going to decrease. Again, sort of assuming we're closer to this end of things. So there's a trade-off there between gain and maximum swing at the input. And that's a zoom in where you can kind of see what's going on with the slope. There's two terms that you should be familiar with, headroom and legroom. Legroom is the term we use to represent the swing, the maximum allowable swing between our operating point and point B, which is the crossover between saturation and triode. And then headroom is the distance between Q and point A. Okay. So, yeah, you have that homework due the last day of class. All right. So we know that if we want to analyze exactly how an amplifier works, we're going to have to use the small signal model, right? It makes sense. The whole idea of the amplifier is based on, large signal and small signal values. We're amplifying the small signal component only. The gain is defined by the large signal component. So, I mean, it shouldn't be any surprise that we're going to use a small signal model to analyze the way that it works. So let's see exactly how to do it. How do we split it up into the two different circuits? How do we represent the MOSFET for large signal versus small signal? For the diode, how do we do that? Right? The large signal component was the constant voltage drop model, so that was like an 0.7 volt drop across it. And then for the small signal component, we linearized it, and it ended up being a resistor, right? An R small value, RD. So how are we going to do that for this one? All right. So the bias point, the large signal value, we're just going to use these equations here. Okay. We'll plug in what our operating point of VGS is, right? This should be given to you, right? This is one of the things that's a parameter of the amplifier. And we plug that in here. That'll give us the large signal component of ID. And we use that in 541. And that'll give us the large signal component of the output, VDS. All right. Now, the small signal component. So what happens when we try to linearize this thing? Or we try to simplify its operation. Or simplify the model, I should say. Okay, 542 up top, same thing we've seen before. We're taking the total value of VGS and we're substituting in large signal plus small signal components. 517 is just taking the VI characteristic for the MOSFET in the saturation region, and instead of having the total value of VGS, we're putting in big VGS plus little VGS. That makes sense. Okay, now what we can do is, right, this is squared. So what if we expand it? And when we expand it, we're going to group VGS minus VT together and little VGS by itself, right? Because if you use FOIL, that's what it's called. FOIL, right? When you multiply like a second order polynomial. Okay, so you need to have two different terms. It's right, like x plus y squared. So our x is going to be VGS minus big VGS minus VT, and then our y is going to be the little VGS. So when we multiply that out, we end up with this. The large signal component squared, a component that's a combination of both the large and the small signal, and then the small signal component squared. And so if I write this out, we see this here. Now, the total instantaneous current is equal to, what is this? This is the same expression we got from the previous page. That's this. It's the large signal value of ID. So the total ID is equal to the large signal value, or the large signal component of ID, plus this component, which has both, and then this. Is this going to be a big or a small value? VGS itself, little vgs, is small. What happens when you take a small value and you square it? It becomes even smaller, right? So with a pretty high level of confidence, we can assume that this last component, the effect of it, is going to be minimal. Which, what it leaves us with is a nice large signal component, small signal component. And here, again, it's linear, the relationship. VGS times a coefficient. Just like how we had 1 over RD for the diode, we can have a 1 over RD. It'll be 1 over RD will be equal to Kn VGS minus VT. Right? That's the relationship between VGS, small VGS, and small ID. So that's what we have here. 3 different terms. We have the DC bias current, the large signal component of the current. We have the linear gain term, which is what we're going to use to build our small signal circuit. Coefficient, which is constant, times little VGS. And then we have our nonlinear distortion term, which we are assuming is just not going to have that much of an effect on what's going on. All right. So we get rid of the third term, and we see that the transconductance value, which is the same as what we called 1 over RD before, but in this case we're going to represent it as a transconductance. We're not going to use a resistor. Either way, it's the ratio between V and I is device transconductance parameter, large signal operating value, a large signal component of VGS minus VT. Okay, so what we see here is that's essentially the slope. And it makes sense because, right, when we calculated the gain was Kn VOV times VDD. This is the slope between V and I, not between V and V, and so it has 2 of the 3 components that we had from when we calculated the gain. All right, so that was how we applied the small signal model to the MOSFET, and now we need to go and apply the small signal model to the amplifier. Some of this is redundant. Okay. You can review those slides if you'd like, but it was just saying a lot of the same things that we had already said. The leg room is going to be the component of the input that mostly determines the swing and what the gain was, right? we'd already defined all of these. The output is going to be shifted from the input by 180 degrees. We already said that the gain was negative. There's not much new in there. We defined the gain as negative GM RD. That's the same as negative KN VOV RD. We've already said all that. Okay, so let's skip forward to the nuts and bolts of how do we draw the circuits, right? Because that's really what you want to know when you do this in practice, you got to take the one circuit, you draw two different circuits from it, and you solve both of those, and you get your answer. So how are we going to do this? For the small signal circuit, what we're going to do is we're going to represent the FET as a voltage-controlled current source. So if you remember the diode, we pulled it out, and we replaced it with a resistor. Now we are going to pull out the FET, and we're going to replace it with a voltage-controlled current source. Right, it accepts the small signal component of VGS between the gate and the source. It provides a value of ID at the drain. The input resistance we can assume is high, and the output resistance we can also assume is high. What's the difference between this and this? I mean, it's written in the caption, but if anybody remembers, we talked about it briefly before. So that RO is only there if we're considering channel length modulation. If you remember, there was three values we could use to define whether channel length modulation was significant. There was VA, there's lambda, and then the last one is the RO, the output resistance value. For most of these problems, we're not going to be considering channel length modulation, so you'll be looking at the top half of the figure as opposed to the bottom half. And where does the GM value come from for this? Comes from here, 547, right? We already, from when we expanded the second order polynomial, we ended up, we saw that the ratio between VGS and ID is going to be equal to this. Kn times whatever the overdrive, the large signal component of the overdrive voltage is. So any resistor value that's less than 1 mega ohm, I would say for this, the purposes of this class, anytime the output resistance is not considered to be infinite, then you're considering some sort of channel length modulation. Okay. Model B is more accurate than Model A. I mean, in reality, there always is some small amount of channel length modulation that's going to be seen in the way that a MOSFET acts. It's just whether it's important enough to the problem in order to take into consideration. And so the main difference is that if our gain will be affected by channel length modulation. And so we have here our value for gain, negative GM times RD. This is without channel length modulation. If we're considering channel length modulation, then you replace RD with the parallel value of the parallel combination of RD and whatever that output resistance is. All right, so some observations from 547 and 547 really being the second part of this here. Again, we used foil. So some observations. GM is proportional to the device transconductance parameter, which in turn is made up of the electron mobility, the oxide capacitance, the aspect ratio. So that is all going to have going to play a role in the gain of the amplifier. So if you're choosing a component, the larger those values are, the more, the greater gain you can get. A MOSFET with a short and wide channel will provide maximum gain, everything else being constant. And we can increase the gain using the large signal component of VGS, but like we said before, that'll have an effect on other things like the swing. I already said the thing about Model B. And we've already. Is this slide in here twice, or did I go backwards by mistake? I guess I went backwards by mistake. Okay. A lot of equations here, different variations on what has already been presented. Like you've seen at several other points in the textbook, they give you different forms of the same equations, which, I mean, they'll be on the cheat sheet and they can be applicable for certain types of problems, but, you know, we can derive this by doing like algebraic combinations of stuff that we have. You can calculate the overdrive voltage from other values. Same thing with calculating the transconductance, et cetera, et cetera. Okay, so now we haven't talked about what a BJT is yet. That's going to be Chapter 6. It's the other type of transistor that we're going to be focusing on, which is the bipolar junction transistor. And if we assume that the DC component or the large signal component of the current is 500 microamps, and that the transconductance, the process transconductance parameter is as shown, you can see how with an aspect ratio of 1, you get a certain transconductance value. With an aspect ratio of 100, you get a larger transconductance value, but the BJT blows them both out of the water. So, you know, we talked about how MOSFETs are the more modern technology and they're used for X, Y, and Z. But one area where the BJT does still pose an advantage over the MOSFET is in the design of certain types of amplifiers, because the gain is higher. Again, 555 and 557, not to minimize it, but it's just different permutations of the same equations. And this slide again, different versions of the same thing. So, I mean, when you do the homework problems, you'll have an opportunity to use all three of those, but I don't really see much point in me deriving it over and over again. So I think you guys get the idea. Okay, example 510.